Welcome to this deep dive into some quite remarkable observations of the galaxy 1ES 1927 plus 654. This galaxy has undergone some dramatic changes between 2018 and 2023, all seemingly tied to its central supermassive black hole. What's particularly interesting here is that we had a series of observations covering the entire period, so we can track how things have changed
That makes this a very special case.
and develop.
Often we only get snapshots of these kinds of events. To see this level of detail over several years is quite fortunate.
So let's start at the beginning. In 2018, astronomers detected a sudden brightening of this galaxy. What exactly happened?
The galaxy's brightness and visible light increased 100-fold in a very short period. Such abrupt changes in brightness are often associated with what we call a tidal disruption event.
Could you elaborate on what a tidal disruption event entails?
Certainly. Imagine an object like a star wandering too close to the supermassive black hole at the center of the galaxy. The immense gravitational pull of the black hole exerts a much stronger force on the side of the star facing it, compared to the side facing away.
So the star experiences a stretching force.
Precisely. And this difference in gravitational force, which we call tidal force, can become so strong that it overwhelms the star's own gravity and tears it apart.
Rather a dramatic end for the star. What happens to the stellar material?
The disrupted material doesn't just vanish. Instead, it spirals inwards towards the black hole, forming what's known as an accretion disk. As the material falls closer to the black hole, friction and gravitational forces heat it up, causing it to release vast amounts of energy across the electromagnetic spectrum, and that's what we observe as a sudden brightening of the galaxy.
So that explains the initial flare in visible light. However, the sources also mention a strange development related to X-ray emissions from the galaxy
Yeah.
around the same time.
Yes, the increase in visible light coincided with a near-total drop in X-ray emissions, which was quite unexpected. Typically, active galaxies like 1ES 1927 plus 664-4 are strong X-ray emitters.
Is it that the X-rays were somehow obscured by the material from the disrupted star?
It's not that simple. We believe that the X-rays are produced by a region of extremely hot electrons called the corona, which is located very close to the black hole. This corona is thought to be powered by the black hole's magnetic field, and the sudden drop in X-rays suggests that something disrupted this corona itself, not just blocked our view of it.
So the tidal disruption event somehow disrupted the black hole's X-ray generating mechanism.
It is.
That seems like a rather significant disruption.
The exact mechanism is still being investigated, but the leading theory is that the sudden influx of material from the disrupted star fundamentally altered the structure of the accretion disk and corona.
Interesting. But the story doesn't end there, does it? The sources indicate that the X-rays eventually returned, but with a twist.
Indeed, after about 100 days, the X-ray emissions did begin to recover, but they came back at a much higher intensity than before the tidal disruption event. It's as though the black hole's X-ray machine was not only repaired, but upgraded.
Perhaps a result of the black hole now being in a more active state,
That's precisely the hypothesis.
having been fed by the material from the disrupted star.
The tidal disruption event likely triggered a transition in the black hole, from a relatively quiet state to a more active one, characterized by increased accretion and energy output.
A change in state triggered by what, from a supermassive black hole's perspective, would be a relatively small snack.
It is rather intriguing. It seems that even a relatively small amount of matter can have a profound impact on the dynamics of a supermassive black hole and its surroundings.
And these observations give us a direct view of that process.
Yes, this is a rare opportunity to observe a black hole transitioning
We see the initial disruption,
from a quiet state to an active one in real time.
the drop in X-rays,
Yeah.
and then the black hole turning on and increasing its activity.
It challenges some of our previous assumptions about how these transitions occur and how much matter is required to trigger them.
This is fascinating. But I understand there's another major development we haven't even touched on yet. In 2023, there was another significant change observed in 1ES 1927 plus 654.
Quite right. This is where things get particularly interesting. The galaxy, which was previously radio quiet, began emitting strong radio waves.
And what does that tell us?
The emergence of strong radio emissions is a telltale sign of the formation of a relativistic jet, a powerful beam of particles being launched from the vicinity of the black hole.
So this supermassive black hole has awakened
Precisely.
and is now launching a jet of material outwards.
And this jet is not just any jet. Observations from the Very Long Baseline Array, or VLBA, revealed two distinct blobs of radio emission moving apart. at nearly 30% the speed of light.
That's astonishingly fast.
It is, and it indicates the immense power of the processes at work near the black hole. The jet is a direct consequence of the black hole transitioning into an active state, fueled by the material from the disrupted star.
So, let me just summarize to make sure I'm following correctly. We have this galaxy, 1ES 1927 plus 654, which undergoes a dramatic brightening in 2018. Due to a star being disrupted by the central black hole, this disruption causes a temporary drop in X-ray emissions, followed by a resurgence of X-rays at a higher intensity, indicating that the black hole has become more active. And then in 2023, the galaxy suddenly starts emitting strong radio waves, a sign that a powerful jet has been launched from the black hole.
That's an excellent summary of the key events so far.
But I have a feeling this is just the beginning of the story. There are still many questions to be answered.
You are absolutely right.
Aren't there?
While we have a good general understanding of the sequence of events, there are details that require further investigation. For example, what caused the X-ray emissions to oscillate?
Yes. The sources mention something about the X-ray intensity changing periodically. That's a puzzle I'm eager to delve into. But perhaps that's a topic for part 2 of our deep dive.
Indeed, it's a detail worth exploring in more depth. Picking up where we left off, let's discuss these oscillating X-ray emissions, as we've established. The X-rays from 1ES 1927 plus 654 came back stronger after the initial disruption. However, they didn't just settle at a new steady level. They began to oscillate in intensity, with a period that has been steadily decreasing over time.
The sources mention that this period went from around 18 minutes down to just 7 minutes over the observation period. What could possibly cause such rapid, regular changes in X-ray output?
It's a fascinating puzzle, and one that has generated considerable debate among astronomers. One of the initial hypotheses was that there might be a smaller object, perhaps a white dwarf or a neutron star, orbiting very close to the black hole.
A survivor of the tidal disruption event. That seems rather improbable,
It does, doesn't it?
given the extreme environment around a supermassive black hole.
But the idea was that this object, a remnant of the disrupted star, could be orbiting the black hole and periodically blocking some of the X-rays, causing the observed oscillations.
Well, a kind of cosmic eclipse, with this smaller object passing between us and the black hole's X-ray corona.
However, for this scenario to work, the object would have to be orbiting incredibly close to the black hole, and the rate at which the oscillation period is decreasing suggests that it would have to be spiraling inwards very quickly.
Wouldn't we expect such an object to be torn apart
That's a valid point.
by the black hole's tidal forces, long before it could complete many orbits?
For an object to survive in such a close orbit, there would need to be a mechanism counteracting the black hole's immense gravity. Some theorists propose that material could be transferred from the object to the black hole, perhaps stabilizing its orbit.
A precarious balancing act, to say the least.
Indeed. And while the survivor hypothesis was initially intriguing, it's becoming increasingly difficult to reconcile with the observational data. The rate of change in the oscillation period is simply too fast, even considering these stabilizing mechanisms.
So if it's not an orbiting object causing these oscillations, what other explanations are being considered?
There are several alternative possibilities, all of which involve complex physics. One idea is that the oscillations are related to the rotation of the black hole itself.
I must confess I'm not quite seeing the connection between a black hole's rotation and variations in its X-ray emissions.
It's a complex phenomenon, but essentially, a spinning black hole drags space-time around with it, a phenomenon known as frame dragging. This twisting of space-time can affect the motion of matter in the accretion disk, potentially causing periodic variations in the X-ray output.
So the oscillations could be a direct consequence of the black hole's spin.
It's one possibility, but there are others. Another intriguing hypothesis involves magnetic reconnection events within the accretion disk.
Please remind me what magnetic reconnection is.
As material spirals inwards towards the black hole, the magnetic field lines within the accretion disk can become tangled and twisted. When these stressed field lines snap and reconnect, they release a burst of energy, which could be the source of the X-ray oscillations.
And if these reconnection events occur periodically,
That's the idea.
they could explain the observed pattern of varying X-ray intensity.
Of course, both the frame dragging and magnetic reconnection hypotheses require further investigation. We need more data, more detailed models to determine which, if either of these mechanisms, is truly at play.
So while we have a good grasp of the overall events, the details of what's happening within the accretion disk, so close to the black hole itself, remain a mystery. But these observations are still providing valuable insights,
Absolutely. The fact that we can observe a black hole transitioning
aren't they?
from a quiet state to an active one and witness these unusual oscillations in X-ray missions is quite extraordinary. It challenges our understanding of black hole behavior and highlights the incredible complexity of these systems.
It's a reminder that despite all our advances in astrophysics, there's still much we don't understand about these cosmic behemoths.
Indeed, and the observations of 1ES 1927 plus 654 are pushing us to refine our models, to ask new questions, and to develop new ways of probing the mysteries of black holes.
So this event, while not fully understood, does give us some important clues about black holes more generally, doesn't it?
Absolutely. One of the key takeaways is that these transitions between quiet and active states are not necessarily gradual processes. They can be triggered by relatively small amounts of matter, as we saw with the tidal disruption event in 1ES 1927 plus 654.
It suggests a certain dynamism, a responsiveness to the environment
Precisely.
that we might not have previously attributed to supermassive black holes.
And it raises fascinating questions about the role these transitions play in the evolution of galaxies.
Do we know how common these transitions are? Is 1ES 1927 plus 654 a unique case? Or are black holes flickering on and off all the time?
It's difficult to say for certain, as these transitions are thought to be relatively brief on cosmic timescales. Catching a black hole in the act of switching states, as we have with 1ES 1927 plus 654, is a matter of both luck and diligence.
We need to be looking in the right place at the right time
Exactly.
and have the right instruments to capture the event.
But based on the limited observations we do have, it seems likely that these transitions are not uncommon. Black holes are not static objects. They are dynamic entities that respond to changes in their surroundings.
So what we're seeing in 1ES 1927 plus 654 could be a glimpse into a process that is happening all across the universe, driving the evolution of galaxies and shaping the cosmic landscape.
That's a very plausible scenario, and it underscores the importance of continued observation and study of these events. Each new observation, each new puzzle brings us closer to understanding the intricate interplay between black holes and the galaxies they inhabit.
This has been a remarkable deep dive so far. We've traced the evolution of this event from the initial brightening to the launch of the jet, and explored some of the leading hypotheses about those mysterious X-ray oscillations.
And yet there's still one more intriguing aspect of this story that we haven't even touched upon, something that challenges our understanding of black holes even further.
You've piqued my curiosity. What is this final piece of the puzzle?
It relates to the very nature of the X-ray oscillations themselves, and what they might tell us about the fundamental properties of the black hole at the heart of 1ES 1927 plus 654.
It sounds like we've only just scratched the surface of this cosmic mystery. I'm eager to hear more, but perhaps we should save that discussion for part 3 of our deep dive.
A wise decision. This final detail deserves our full attention.
We've reached the final part of our deep dive into the fascinating events surrounding Galaxy 1ES 1927 plus 654. We've covered the tidal disruption of it, the emergence of the jet, and discussed those puzzling X-ray oscillations. You hinted that there's one more layer
Indeed.
to this cosmic onion, something that pushes our understanding of black holes even further.
All of the observations we've discussed so far, while remarkable, are largely consistent with our current models of black hole behavior, even if they test the limits of those models. However, there's one aspect of the X-ray oscillations that presents a real challenge.
You mentioned earlier that the rate at which the oscillation period is decreasing is a problem for some of the proposed explanations. Could you elaborate on that?
Certainly. Remember, the period of these oscillations has been steadily decreasing from around 18 minutes down to just 7 minutes over the course of a few years. This rate of change is much faster than our models predict for any object orbiting that close to a supermassive black hole. Even considering mechanisms that might temporarily stabilize such an orbit.
So even with material being transferred from the object to the black hole,
That's the current thinking.
it should still spiral inwards, more slowly than the observations suggest.
This rapid change in the oscillation period is very difficult to explain. If we assume the oscillations are caused by an orbiting object, it raises the possibility that something else entirely is driving these periodic variations in X-ray intensity.
This brings us back to those alternative explanations, the black hole's rotation, or perhaps magnetic reconnection events in the accretion disk. Do those hypotheses offer a better fit for this rapid change
They might,
in oscillation period?
although the physics involved are complex and not fully understood. If the oscillations are linked to the black hole's rotation, this rapid change in period could tell us something about the black hole's spin, or perhaps about changes in the structure of the inner accretion disk.
Is it possible that the black hole's spin could be changing over time?
It's not impossible, although it would require a significant transfer of angular momentum, perhaps through interactions with the accretion disk itself. This is an area of active research. And there are theoretical models that explore how a black hole spin can evolve over time.
So we could be witnessing a dynamic process where not only is the black hole's activity level changing,
That's one possibility.
but its fundamental properties like its spin are evolving as well.
And it highlights how much we still have to learn about these extraordinary objects. The other hypothesis involving magnetic reconnection events could also potentially explain the rapid change in oscillation period. If the frequency of these reconnection events is increasing, that could lead to the observed decrease in the oscillation period.
Would an increase in the frequency of magnetic reconnection events be expected
It's plausible.
in a system like this, where a black hole has recently transitioned to a more active state?
The increased accretion rate and the associated changes in the structure of the magnetic field around the black hole could create conditions that are more favorable for magnetic reconnection to occur.
So while the exact mechanism driving these X-ray oscillations remains uncertain,
Precisely.
the fact that their period is changing so rapidly presents a significant challenge to our current understanding of black hole behavior.
These observations are pushing the boundaries of our knowledge and forcing us to reconsider some of our assumptions about the physics at play in these extreme environments.
It's a reminder that the universe is full of surprises,
Indeed.
and that even the most well-established theories can be challenged by new observations.
And that's what makes science so exciting. We are constantly refining our understanding of the cosmos, and each new discovery opens up new avenues for exploration.
So what's next for the study of 1ES 1927 plus 654? What are astronomers hoping to learn from continued observations?
Continued monitoring of this galaxy across multiple wavelengths will be crucial. We need to gather more data on the X-ray oscillations, track the evolution of the jet, and search for any other signs of unusual activity.
I imagine theoretical work will be just as important as observational data
Absolutely.
in trying to untangle this cosmic knot.
Theorists are developing new models, incorporating the latest data from 1ES 1927 plus 654 and other similar events, to try to explain these observations and to refine our understanding of black hole physics.
It's clear that we are just at the beginning of unraveling the mysteries of 1ES 1927 plus 654. This event has already taught us a great deal about black hole behavior, and I suspect it will continue to yield valuable insights for many years to come.
It's a case study in the power of astronomical observation and the ever-evolving nature of our understanding of the universe. Each new discovery brings us closer to comprehending the vastness and complexity of the cosmos and reminds us of the endless wonders that await those who dare look up at the night sky and wonder.